Hey everyone, and welcome back to The Explainer. This one is brought to you by Forge College. So, in our last lesson, we were flying high, right? We were configuring those high-speed Solana AI tooling plugins, talking about rapid integration and high-level architecture. But today, we're doing a complete 180. I need you to completely switch gears. We are going to pop the back off the EVM pocket watch, grab our jeweler's loop, and look directly at the meticulous, microscopic, gas-guzzling gears of the Ethereum virtual machine. We're diving into practical opcode tracing. Here is our engineering blueprint for today's session. We're going to run through EVM forensics, setting up the lab, the step-by-step trace, catching constraints, and finally, putting together your debug report. Let's get to work. All right, Section 1, EVM forensics. From abstract to concrete. We're bridging the gap here between high-level theory and actual real-world mechanics. Now, as a developer, you've likely spent a good chunk of time studying the EVM's theoretical constraints, right? You know all about gas limits, stack depth, and valid jump destinations. But the real forensic question is, how do we actually go from those abstract rules to the runtime mechanics? How do we watch this invisible mathematical brain do its thinking without just guessing? Think of it like comparing the rulebook to the actual game tape. On one hand, we have the abstract rules we've studied, things like gas accounting or stack framing. But on the other, we have our concrete trace. This is your tangible forensic evidence. We're talking about moment-by-moment state changes, program counters, exact memory snapshots. Tracing literally makes the invisible visible. And honestly, it's the exact skill you need when a smart contract inexplicably fails, burns thousands of dollars in gas, and you need to prove exactly why it happened. Moving on to Section 2, setting up the lab. To do this kind of microscopic forensic work, we need a clean workspace. Let's grab those virtual mechanics goggles. We're going to build a really minimal local Node.js tracing environment. It just takes a few terminal commands. We'll make a directory called EVM trace, initialize a new node project, and install ethereumjs-vm along with buffer. Why so minimal? Because by doing this, we completely silence all the background noise of a full blockchain node. We want to focus entirely on pure raw code execution without any distractions. And here is our specimen for today. It's this compact little string of hex-encoded bytecode, starting with 6005, 600401. Now, despite being tiny, it is a fantastic example. It perfectly demonstrates a sequence of essential operations. We've got push instructions to load data, an add instruction for arithmetic, a jump I for conditional control flow, an mstore to write to memory, and finally a return. It is basically the perfect microscopic organism for our test bench. To actually observe this bytecode running, we're going to write a simple JavaScript runner. The secret sauce here is the on-step event listener. Think of this exactly like hooking up an OBD2 diagnostic scanner to your car's engine. For every single turn of the internal gears, literally every single instruction, our script hooks directly into the virtual machine to emit a log. It grabs the program counter, the opcode mnemonic, the state of the stack, a hex dump of memory, and exactly how much gas is left in the tank. Which brings us to Section 3, the step-by-step trace. We have our lab, we have our specimen, the diagnostic scanner is plugged in. Let's fire up the machine and look at the output ledger. Okay, here is the raw output from the very beginning of our trace. Notice the program counter, the PC, starting right at 0. We execute a push1 opcode. And boom, the value 0x05 appears neatly on our stack snapshot. Then, at PC2, another push1 hits. Now our stack reads 0x04, followed by 0x05. Remember, we always read the stack top to bottom. That is absolutely crucial for understanding what happens next. Because at PC4, we run into the add opcode. Remember those two values just sitting on the stack? The add opcode gracefully consumes the top two items, the 0x04 and the 0x05, and replaces them with a single result, 0x09. You are literally watching those abstract stack framing rules being enforced in real time. If there was only one item on that stack, the machine would have violently thrown an underflow error right in our faces. Section 4, catching constraints in action. Let's go hunting for those critical moments where the EVM acts as a strict referee, enforcing its non-negotiable laws. Check out this conditional jump, the jump opcode at PC7. The EVM checks the stack for two things here, a destination indexed and a condition value. But it doesn't just blindly jump. It enforces a really critical constraint. The destination index absolutely must point to a valid jump dest opcode. And here, we can verify that after the jump by executes, the very next program counter logged is 10, which perfectly matches our valid jump test. If it pointed anywhere else, the trace would immediately crash with an invalid jump exception. It does not mess around. Now, I want you to focus heavily on this number, 999,850. This is the gas remaining directly after our store instruction fires. In our earlier steps, the gas was only dropping by maybe 3 or 10 units at a time, but here, a sudden massive drop. Why? Because writing to memory is expensive. The EVM is acting as a strict accountant here, charging us a premium for expanding our active memory footprint. So, when you are reviewing your own trace logs out in the wild, these are the 3 main constraint behaviors you really need to hunt for. Number 1, look for sudden gas reductions from heavy opcodes like mstore, ssstore, or call. Number 2, check jump validity. Did control flow change smoothly or did it crash? And number 3, always monitor stack framing to ensure opcodes have exactly what they need to avoid underflows. This is exactly how you catch the culprits that are draining your contract's lifeblood. All right, Section 5, the debug report. Analyzing the trace is a lot of fun, but we actually need to document what we found. It's time to package up all this raw forensic data into a professional, tangible artifact. To write a really effective debug report, you've got to hit 3 distinct success criteria. First up, verify trace completeness, meaning ensure your log actually ends with a return opcode or an explicit exception, not just cutting off. Second, you need to provide 3 precisely annotated snapshots from your trace, proving exactly what the stack and memory looked like at critical boundaries. And finally, identify 2 specific examples where constraints like gas limits or jump validity visibly altered the machine's behavior. Honestly, the whole process is perfectly summarized by this quote. Every instruction's precondition must be evidenced in the trace. You can't just guess why a contract behaved a certain way. You've got to bring receipts. You must provide concrete proof by quoting the exact program counters where a specific constraint dictated the machine's behavior. Getting into that habit is what turns you from a code guesser into a true Web3 forensic analyst. But that leaves us with a pretty fascinating question. What actually happens to the trace when the machine violently breaks down due to an out-of-gas or invalid jump error in a massive, complex smart contract? Well, you'll just have to join us for our next lesson, Diagnosing Execution Constraints, where we tackle exactly that scenario. Make sure to bring your completed debug reports to that session. And as always, to dive deeper into this subject and master more Web3 concepts, definitely go visit us at forge.college. Thanks so much for joining me on The Explainer today, and keep tracing.